Hey, Algebra 2. We're going to talk about Lesson 20. Lesson 20 and 21 are going to go hand in hand. They're separate lessons, but it's really splitting one lesson into 2 days. It's modeling riverbeds with polynomials. So we're going to touch on the first, and then we're going to move on to using the remainder theorem to solve systems of equations, or to come up with a polynomial, using the remainder theorem to be able to come up with a polynomial given a set of points. First of all, the Environmental Protection Agency is studying the flow of a river in order to establish flood zones. The EPA hired a surveying company to determine the flow rate of the river, measured as volume of water per minute. Okay, that's supposed to be an underline, not a cross out. The firm has set up a coordinate system and found the depths of the river at 5 locations, as shown on the graph below. After studying the data, the firm decided to model the riverbed with a polynomial function and divide the cross-sectional area into 6 regions that are either trapezoidal or triangular, so that the overall area can be easily estimated. The firm needs to approximate the depth of the river at 2 more data points in order to do this. Okay, we have 2 more data points where the firm has to approximate the depth of the river. Let's talk for a little bit. That's all your paper shows you. My lesson has much more information. So pertinent vocabulary: flow rate, or volumetric flow rate. It's the volume of fluid that passes through a given surface per unit of time. I've got a drawing that I'll show you. We basically see the riverbed. So this would be my surface, and it's the volume of water that flows through that surface per unit of time. A riverbed is the channel in which the river flows. Okay, a riverbed is not symmetrical by any means. It's however the river moves the particles along the bottom of the bed. And goodness, if trash is in there, if a boat's in the bottom, etc. So the riverbed, it's the channel in which a river flows. And then cross section, that's what we've done right here. A 2-dimensional view of a slice through an object. Okay, the next drawing is actually much cooler. So I'm going to erase this one and this one. Probably could have done that a lot faster. Okay, there's our very cool riverbed. I always move that first, don't I? And the dark blue right there is the cross section. The shape that we see there is the channel. So there's our channel. This is a cross section, etc. But let's erase that. Come back. Goodness. There we go. All right, so what is our goal in this modeling exercise? Okay, what do you think the goal is? Reread the problem. What's it asking you to do? We need to find the flow rate of water through the riverbed. How can we estimate the flow rate of water? If we knew what the area was of the cross section, if we could figure out this area, if we knew the area of the cross section and the speed of water, then the flow rate is the product of the cross-sectional area in square feet and the speed of water. So let's write that down. Okay. Area of cross-section and current speed of water. So we know the flow rate is the product, which is multiplication of the cross-sectional area in square feet and the speed of water in feet per second. Okay, to estimate the area of the cross-section, what information do we need? We need more data points. So we need enough data points to make a good estimate. To gather enough data points, we will need to make an assumption that the riverbed changes smoothly between the data points we have. With that assumption, we could estimate other data points by approximating the curve of the cross-section using a polynomial function. We need to sort of connect the points on the graph that we have. So that is our first task. We need to find a polynomial function equation, right, to fit the data. We've done that in the past using our graphing calculator. Today we're going to do it by hand. I know we give you technology and then we take it away. All right, draw the graph of a polynomial function that passes through the 5 given data points. So I'm pretty sure I put the one the book did in here, but I'm going to go ahead and draw a curved function. Now draw the 4 trapezoids and the 2 triangles that will be used to estimate the cross-sectional area of the riverbed. I would use a straight edge and a pencil if I were you. I'm going to do my best. There's my first triangle. Beautiful, I know. There's my second triangle. And now I'm going to do my trapezoids. One, 2, 3, 4. So I have 4 trapezoids and 2 triangles. And if I can do the area of the 4 trapezoids and the area of the 2 triangles and add those areas together, that would be the cross-sectional surface area of my riverbed. Okay, but we are going to use the points that we found and come up with an equation for this. Not right now, but we will. Okay, we have 5 data points, right? What information are we missing? If you go back, you actually have it in front of you. We're missing the depths. So if this was my graph, that's wrong. You know, we're like this. We're missing the depth at x equals 40 and x equals, I think, 80. So what information are we missing? The depths at x equals 40 and 80. How can we find the missing values? If we had a polynomial function, p, that fits the given data, and then we use that equation to find p of 40 and p at 80, that would give us a good estimate of the depths. So we need to find a polynomial function that represents our data. Okay, and then once we have that function, we would evaluate that function at 40 and 80 to give us an estimate of our depths. Right, what is the lowest degree polynomial that could be used to model this data? One way we can figure that out is looking at the relative maximums and minimums. I have three relative maximum and minimum points. So I'm thinking this might be a degree 4. Okay, what constraints must our polynomial meet? We know a few of our points. We know that p evaluated at 0 is 0, p evaluated at 20 is negative 20, p evaluated at 60 is negative 15, and p evaluated at 100 is, oh goodness, we actually have a lot of points, negative 25. P at 120 is also 0. Those are our constraints. Those are the dots, the points that were given in the graph itself. We were given 1, 2, 3, 4, 5 points. Okay. All right, we're going to put a pause on that modeling for now and continue on with it tomorrow. Okay. Now let's get to our example. Okay, we're going to work this example two ways. First, we're going to solve this using a system of equations. Then we are going to use the remainder theorem. I won't lie, I find the remainder theorem difficult just because that's not how I was taught. So I'm hoping if we take time to teach you guys the remainder theorem that one or two of you may really enjoy it and understand it to use it, right? Okay, let's ask some questions first. Will the polynomial function that we find through these points be linear? Okay, I have 3 points. One's up there, one's down there, and one's over here. Not a chance. Okay, it should not be linear. It can't be linear just because there's just 3 points. If I'd only given you 2, yes, definitely linear, but with there being 3 points, it's definitely not linear. Okay, what do you think the lowest degree polynomial we can find that passes through 3 points is? Okay, if we have 3 points, then we're going to try to fit a quadratic polynomial, which, well, that's all right. So that is, they're going to seem to lie on a parabola. Okay, I'm given 3 points, so it appears we could fit a quadratic polynomial to these points. Okay, so we're going to try to find a quadratic polynomial whose graph passes through these points. That's what we're going to work through. Okay, so the form we're going to look at is this. Right? So that's what we're going to use here on the next few slides. All right, so first we're going to solve this using a system of equations. Okay, we're going to take the points that were given and just plug them into an equation to see if we can solve the equation. First, we're going to start with p of 0 equals 28. And I'm plugging it into, oh goodness, every time, right? Ignore this. I'm plugging it into p of x equals ax squared plus bx plus c. Okay, we actually don't need this graph. And so let's just look at this. So remember, we have this being our x and this is our y. So let's go ahead and plug it in. If we plug in 0 for all the x's, we're going to have a times 0 squared plus b times 0 plus c equals 28. That means that we have c equals 28. We know one of our constants. That's great. Let's try the next one. P of 2 equals 0. So let's go ahead and plug it in. We have a times 2 squared is 4, plus b times 2 plus 28 equals 0. Let's go ahead and simplify. 4a plus 2b equals negative 28. Let's go ahead and factor a 2 out. See if we can simplify this at all. That gives us 2a plus b equals negative 14. So we're going to use this. And now let's look at p of 8 equals 12. So a times 64 plus b times 8 plus 28 equals 12. 64 plus 8b plus 28 equals 12. I'm going to continue right over here. Subtract 28 from both sides. Oops, I forgot an a right here. 64a plus 8b equals 12 minus 28, negative 16. I'm going to factor out an 8. So 8a plus b equals negative 16. That simplifies to 8a plus b equals negative 2. Okay, now I need to grab these two equations and subtract them. So I'm going to take 8a plus b equals negative 2 and subtract 2a plus b equals negative 14. 8a minus 2a is 6a, b minus b is 0, yay. Negative 2 minus negative 14 is 12, so a equals 2. Plug that back into another equation. Pick one. I'll plug it back into 8a plus b equals negative 2. So 8 times 2 plus b equals negative 2. 16, so b equals negative 18. Okay, you have all of that written down. I need a new slide. So we know that c equals, what do we find for c at the beginning? 28. B equals negative 18, and a equals 2. That gives us an equation. 2x squared minus 18x plus 28. We should check our points. Our points were p of 0 equals 28. Oops. So if we look, I cross off these because they're 0, I'm going to have 28. That one checks out. The second one we had was p of 2 equals 0. So if I go ahead and plug in 2 for x, I'd have x times x is 4 times 2 is 8, minus 18 times 2 is 36, plus 28 is in fact 0. And the last one I had was p of 8 equals 12. 8 squared is 64 times 2 is 128 minus 18 times 8. I don't know off the top of my head. 18 times 8 is 144 plus 28. Let's just double check that. Minus 144 plus 28 is in fact 12. Nice work. Okay, the next thing we need to do is the same problem using the remainder theorem. So I'm going to write down the problem again. P of 0 equals 28. Good goodness, P of 0 equals 28, P of 2 equals 0, and P of 8 equals 12. This is slightly confusing, so I'm going to take my time, and I would expect you to work along with me. Okay, it took me a while to figure this out this morning, to learn it, because I had never done it before, so let's be patient. Okay, the first thing we're going to do is just attack the P of 0 equals 28, and we're using the remainder theorem, so we know that P of x equals x minus 0, which we got right there, times a of x plus 28. Okay, that's the whole, I'll write it down here and then erase it. We talked about, let me see where my original notes are. The quotient and the remainder. There we go. The remainder theorem was the quotient times a factor plus the polynomial evaluated at a of the factor. So this is what we're working with in a slightly different order, but I just wanted to show you what we were working with. And I need lots of room here, so we're going to go ahead and erase that. All right, so P of x equals x minus 0 times a of x plus 28. Simplify that a little bit, and we get x times a of x plus 28. Okay, something that's really cool that we know. We know this equation is quadratic, so we know that P is quadratic. So A must be linear, must be one less. All right, so we're going to use the second point. P of 2 equals 0. Okay, plug that in. I'm going to write this right here. I'm going to use this equation, so I'm going to circle it so I can find it again. So P of 2 equals 0. Let's go ahead and use that. P of 2 equals 2, A of 2 plus 28, and that equals 0. So we just used this 2 and the 0. We plugged 2 in for x, and it was equal to 0 because that's what the remainder theorem tells us. Okay? All right, let's simplify a little bit. We get 2 times a of 2 is equal to negative 28. Therefore, a of 2 equals negative 14. All right, so the remainder theorem tells us that for some polynomial b, we have a of x equals x minus 2. Again, we just got that 2 from here, times b of x minus 14. Okay, we're using that remainder theorem form. All right, so now what do we know about the polynomial b? If we know that p is a quadratic, a must be linear, and b must be a constant. All right, let's use that. So we're going to rewrite P in terms of B. So we're going to take our equation up here and rewrite it. So I have P of x equals x, and then instead of a of x, we just wrote this equation. Instead of ax, we're going to write x minus 2, b of x minus 14 in brackets plus 28. That should be an x. Okay, you guys are cool. I need another page. So I'm going to rewrite this on my next page so I can use it. Third data point. We know that p of 8 equals 12. So let's go ahead and use that. P of 8 equals 8, bracket, 8 minus 2, b of 8, minus 14, brackets, plus 28 equals 12. All I did was for all the x's, I replaced them with 8s. Okay? Let's simplify. 8 minus 2 is 6. This is where I make mistakes. So I'm going to tell you to slow down and make sure you pay attention to all your brackets. Okay, 6 times 8 is 48. 14 times 8, I don't know. So I just distributed that 8. Then I have plus 28 equals 12. Negative 112 plus 28 is negative 84. Negative 84. Add 84 to both sides. I have 96. Divide both sides by 48. And I have 2. Very exciting. All right, go back to our beginning, and we're actually done. P of x equals x, bracket, x minus 2. And instead of b of x, we can write a 2, minus 14, plus 28. Okay, to get our final answer, we do need to simplify this, or to get into something that makes sense. I need one more piece of paper. Okay, let's simplify this. I'm going to distribute that 2 first. 2x minus 4 minus 14. I'm still working within this bracket. 2x minus 18. I've got an x out here. Distribute that x. 2x squared minus 18x plus 28. And I made one mistake. That plus 28 should be a minus 28. No. It's a plus 28. We're good. Okay, we're going to do one more of those. And I know they take a long time, but it's really going to benefit you. Some questions. What if we wanted to fit a polynomial function to 2 data points? If I have 2 data points, what would the lowest degree of a polynomial that fits the 2 data points? Okay. Really, if we only have 2 data points, it would be linear. It would be a line. In the next example, we're going to have 4 data points. And we're going to try to fit it to a cubic example. Okay. Okay, example 2. The book gave you this really nice table to do all your work in. Excuse me. I'm going to have a very hard time fitting work into this table. So I'm going to start a new page and work from that new page. This table does help keep everything organized, where on the previous 3 slides, I tried to keep everything organized and it was sort of difficult to do. So let's go ahead and try this problem. Okay, so we have, I'm going to start out with point the polynomial at -1 equals -3. So when I did this problem, I started out with 0, and you can start out with any point you want, actually. You do not have to follow along with what I've done. So I'll go ahead and start with the point at -1 though. So if we go ahead and put it into the remainder theorem form, since this is -1, we are going to do x plus 1, a of x, minus 3. Okay, so that's our original form. Now let's go down to the next one. We're going to do p of 0 equals -2. So we go ahead and plug that in, and we have 0 plus 1, oh, there's a 1 there. 0 plus 1, a of 0, minus 3 equals -2. And a little reminder, the 0 I put right there, the -2 is what it's equal to. That's the remainder theorem, remember? Go ahead and simplify this a little bit. Excuse me. 0 plus 1 is 1, so we have a of 0 equals, add 3 to both sides, 1. Go ahead and rewrite what our a of x is. X times, hold on, x b of x plus 1. I'm actually going to erase that and make that my step 2. I don't want to miss a step here. So we have x plus 0, b of x, plus 1. Okay, that simplifies to x b of x plus 1. So this right here is what we are going to replace in our original equation. Okay, let's go ahead and try it. Our new function is p of x equals x plus 1, which I got from right here. This is what I'm working with right there. X plus 1, and instead of a of x, I have to write x b of x plus 1 minus 3. Cool, let's go again. P of 1 equals -1. Let's go ahead and plug that in. I have 1 plus 1, brackets, hold on, 1 times b of 1 plus 1 minus 3 equals -1. So this is what I put in for our x, and this is what I put in over here. Okay, I should color code correctly. There we go. So let's do a little simplifying. 1 plus 1 is 2. B evaluated at 1 plus 1 minus 3 equals -1. Distribute that 2. I have 2. B of 1 plus 2 minus 3 equals -1. Go ahead and take those constants to the other side. 2 minus 3 is -1. So add 1 to both sides and I get 0. So b of 1 equals 0. And that's not right. So let's find our mistake. This is always fun, right? All right, so I plugged in 1. I got 1 plus 1 is 2. 1 times b of 1 plus 1. Minus 3 equals -1. Okay, so this simplifies there. That's there. This 2 distributes through. And I have 2 times b of 1 plus 2, because 1 minus 3, oh, no, sorry, I distributed. So that's plus 2. Minus 3 equals -1. So plus 2 minus 3 is -1. Add 1, you get 0. All right, I'm going to push pause and try to find my mistake because it's there somewhere. And you guys have probably already found it by now, but I haven't. So hold on. I can't find it, so we're going with it, okay? Let's rewrite our equation. So we need our b of x equals x minus 1 times c of x plus 0. Okay, now I need to take this equation and replace it right there. I'm going to do that on the next page though. Okay, let me make sure I'm doing, yep, x minus 1, c of x. All right. I copied these two things over from the previous slide. This should be nothing new to what you have on your paper, but I just want to show you what I'm going to replace. So our new p of x is x plus 1, bracket, x. I'm going to do another bracket instead of b of x. Instead of b of x, I need to write this equation. X minus 1 c of x plus 1 minus 3. Okay, double check everything. I just need to put parentheses there. Awesome. Okay, last point. It's getting a little loud, sorry. P of 2 equals 6. So we have 2 plus 1. 2. Excuse me. 2 minus 1. C at 2 plus 1 minus 3. Okay, lots of simplifying to do. I usually start in the inside. So 2 minus 1 is 1. C of 2, I'm still in brackets. I have a 2 on the outside. Plus 1. Here, I'm going to distribute that 2. It becomes a 2. C of 2 plus 1. Two plus 1 is 3. Carry these down. Okay, I think I'm doing everything PEMDAS. Let's distribute that 3. So I have 6. C evaluated 2 plus 3. I can take that bracket down. Minus 3. I forgot to do equals. Oh, but the equals does not go there. These cancel out. I have 6. C of 2 equals 6. So C of 2 equals 1. And that last one is our constant. So we're actually good. We can write our final equation. X plus 1, X minus 1. Oh, that doesn't go there. Hold on. X minus 1. C of 1 is 1, which I know I don't need to write, but I'm just showing you it's there. And that is our final equation, which needs to be written in standard form. So next slide. Okay, let's simplify this. I have x plus 1, and here this all works out into x squared minus x plus 1 minus 3. I can FOIL that, not FOIL it. I'm going to multiply all that together. I get x cubed minus x squared plus x squared minus x plus 1 minus 3. I can cancel out these and those. I'm left with x cubed minus 2. That was a lot of work for that. Let's check our points. P of -1 equals negative 1 cubed minus 2. P of 0 equals 0 minus 2. P of 1 equals, and P of 2 equals 8 minus 2. That was a lot of work. Okay, your lesson summary. I just want to make sure that we all remember a linear polynomial would be determined if you have 2 points on the graph. A degree of 2 polynomial if you have 3 points on the graph. 3 polynomial, 4 points. 4 polynomial, 5 points. The remainder theorem can be used to find a polynomial p whose graph will pass through a given set of points. So it's really important. We've used 2 methods. We solved a system of equation first, and then we used the remainder theorem, which honestly is just going to take a little bit of practice. I'd like you to try it on your homework when it tells you to see if you can figure it out and like it. It's actually sort of fun once you figure it out. Good job today.